One last video on 8.6. In the previous two videos, we learned a lot about parameterizing curves. We first spent a lot of time parameterizing linear equations, and then in what I titled nonlinear equations, we spent a lot of time parameterizing a circle. But really, there's other nonlinear equations that I didn't get to in the last video because there was so much information in the last video that I want to show you in this video. The good news is I don't think any of it is quite as difficult as the stuff we did in the previous video. The first example I want to show you is just figuring out a parameterization for x squared plus 4y squared equals 36. It turns out that this is not the equation of a circle, but rather the equation of an ellipse, kind of an oval looking thing, but you don't need to know any of that to do this problem. It's also worth pointing out that this is not one of those parameterizations where we're specifying the starting and ending points, or how long it takes to do a lap, or what direction we're traveling in. Any parameterization will do down here. So what do? Well, the trick's going to be really similar to what we did when we were trying to parameterize a circle. First, we set the equation equal to 1, so we divided both sides by 36, giving us x squared over 36 plus 4y squared over 36 is equal to 1. And then we rewrote each of these terms so that they were something squared. So in this first case, because 36 is 6 squared, I can rewrite this as x over 6 squared. And in this second case, 4 times y squared is the same as 2y, all in parentheses, squared. And as we saw earlier, 36 is 6 squared, so I can rewrite this as 2y over 6 squared. And that's equal to 1. Why is it so important that it's equal to 1? Because now we can use our Pythagorean identity that sine of some angle squared plus cosine of some angle squared is always equal to 1. So I can choose between these two parentheses and set one equal to sine of t and the other one equal to cosine of t. Either way works, but a little hint from your teacher is always set your x coordinate equal to cosine. It'll make things easier. So the cosine of t would be equal to x over 6, and the sine of t would be equal to 2y over 6. I'm not quite parameterized yet. To do so, I need to solve for x and y, but I'm almost there. Over here, just multiply both sides by 6, and we get x is equal to 6 times the cosine of t. Over here, multiply both sides by 6 and then divide by 2, maybe, and we get that y is equal to 3 times the sine of t. It might not be obvious that this equation right here is an ellipse, but maybe when things are parameterized, it's a little bit easier to see that we have an ellipse. If the x-coordinate were just the cosine of t and the y-coordinate were just the sine of t, we'd have our unit circle here. But it's not. Our x-coordinate is 6 times the cosine of t. So instead of starting out with an x-coordinate of 1, we're going to start out with an x-coordinate of 6. And when t is equal to pi, instead of our x-coordinate being equal to -1, it's going to be equal to -6. Similarly, for sine, when t is equal to pi over 2, we're used to being up here with the height of 1, but our y-coordinate's not just going to be 1, it's going to be 3 times that 1. What I'm saying is that at pi over 2, we'll be up here at positive 3. And at 3 pi over 2, we'll be down here at -3. And if I try my best to connect these dots, with roughly the shape that we get from cosine of t and sine of t, except stretched by factors of 3 and 6 respectively, we get this oval-looking shape, best I can draw it anyways, aka an ellipse. Okay, cool, I guess, whatever. The next thing I want to show you goes all the way back to the first video I made in this section. Maybe you remember this parameterization where x were equal to t squared and y were equal to t cubed, and we plotted some points and came up with this curve that kind of sort of looks like this, tracking the movement of this particle as it kind of slows down and then speeds back up. You might wonder what the equation of this curve in its standard or non-parameterized form would be equal to. If we were going to write this as a function, typically we write y in terms of x, but that wouldn't work here because this graph doesn't represent a function because it doesn't pass the vertical line test. So it'd be hard to write y in terms of x, but it turns out that we could write x in terms of y. And that's exactly what we're being asked to do here. We're given this parameterization right here where the x-coordinate is t squared and the y-coordinate is t cubed. And what we're supposed to do is write x equals something, and that something should just be in terms of the letter y. When you're asked to do that, since we want to end up with x equals something, what we should do is take the other letter, y in this case, and solve that letter for t. So if y equals t cubed, I can take the cubed root of both sides of the equation to get that t is the cubed root of y. That's beneficial because I already know that x is t squared, and now that I can rewrite t in terms of y, I could say that x is equal to the cubed root of y squared. If you're really good with switching radical form to exponent notation, we could say that x is equal to y raised up to the 2/3 power. If you're wondering what this graph would look like, what it looks like to keep track of all the x and y values so that x is equal to y raised up to the 2/3 power, all we have to do is pull out a graphing system, and we see that x equals y to the 2/3 looks like this. It's the same graph we saw back in the first video when we limited the values of t to just give us some portion of that curve. Okay, maybe that's somewhat interesting. Example 3 is a lot like example 2, except I don't want to start out with this parameterization where x equals t squared and y equals t cubed. What I instead want to start out with is x equals the natural log of 3t and y equals the natural log of 6t. So I start out in my parameterized form, and I want it in a more standard form where I'm writing y in terms of x. Note that before I wrote x in terms of y. I had x equals something. Down here, I want it to be y equals something. Up here, when it was x equals something, my strategy was to take the other letter, y in this case, and solve that for t. So down here, where I want it to be y equals something, I'm going to take my other letter, x in this case, and solve this for t. But how do you solve x equals the natural log of 3t for t? Well, the answer is you have to be really good with logs and recognize that x equals the natural log of 3t in logarithmic form is the same as e to the x power equals 3t. I bet when you took a log class you knew this fact, even though it's probably been a long time, and in my experience people don't retain their knowledge from log classes very well. At any rate, I almost have t all by itself. I just have to divide both sides of the equation by t, or maybe instead I'll multiply both sides of the equation by 1/3 and get that t is equal to 1/3 times e to the x power. Now that I've solved for t in terms of x, I can come over here to my equation, which gives me y in terms of t, and change all the t's into that expression that I have in terms of x to get y written in terms of x. So I got the natural log of something. That something is 6 times t. However, instead of writing the letter t, I'm going to write 1/3 e to the x power to get this huge mess. In a sense, I'm done. I've written y in terms of x. You could call this good. It's just not simplified. This is going to simplify really nicely, and I should go through and do that. The first thing to recognize is 6 times 1/3 is just 2. So this is really just saying that y is equal to the natural log of 2e to the x power. And if you remember log rules, specifically that the log of a product, like a times b, is equal to the sum of the two logs, log of a plus log of b, we can rewrite this expression as the natural log of 2 plus the natural log of e to the x. And then one more if you remember kind of thing, because the natural log is the log base e, the natural log of e to the x would just be equal to x, so y is equal to the natural log of 2 plus x. I suppose any of these are okay for an answer, but this one I would argue is the prettiest and maybe the most simplified version. I did this problem because you're going to see a problem really similar on your homework. In this problem, I used this log rule. On the one on your homework, I think you're going to use the fact that if you have a constant times the log of something, you can rewrite that as the log of that something raised up to the power of that constant. So while I didn't use this log rule in this problem, it's something I wanted to remind you of because I think you'll end up using it in your homework. The other thing I want to point out is the natural log of e to the x is just equal to x. That's a simplification that I did here. That also won't be useful in your homework, but a fact that's very similar, that e raised up to the natural log of x is just equal to x, will be useful in your homework. So before ending this video, I wanted to point that out as well. I think that's all that I have. That's a lot on parameterized curves.